to talk about something that we call the electric square. It's a way to take a look at electric force, electric field, electric potential, electric energy, and how to compare all of those. And I'm going to do this from a more algebra-based approach. To see where these all come from, it really needs to be from a full calculus derivation. But for an algebra-based approach, this will work fine. So I'm going to start on the upper left with the electric force. Sort of a main tenet of kinematics and dynamics and where you are in first semester physics. When we look at force being applied to a charge. And that force is going to be the charge times the electric field. Now, from this we actually really can get a definition of what do we mean by field. Well, we can go and we'll come down and we'll divide by charge Q. So 1 over Q. And really that's the definition of field. The electric field is equal to the electric force, the force that a charge experiences, divided by that amount of charge. So this is now the field is a representation of what is happening in that space due to some collection of charges that's nearby. How would another charge, little charge Q, be impacted by that? So that's already the first two of our terms, but now we need to bring in energy and potential. So when we consider force, we know from physics that we can determine the amount of work that is done on a charge. We can say that if we apply this force over some displacement delta x, then we can say that some amount of work has been done. And if all of that work goes into bringing the charge to a higher potential, for instance, then we know that we've stored some electric potential energy. So what I can do here is I can say, well, let's multiply by delta x. Then we can say F E is equal to, or I should say we have Q times E times delta S, x, a force times the distance, is the amount of energy that we store. We're going to look at this in terms of energy. I'll use a more standard U for potential energy. And we'll say that this is Q, it's force times distance, which is Q times E times delta x. Then we can sort of complete what's going on here by saying, well, we can do the same thing here. We can multiply by delta x. So we can do the same thing up here and divide by q. So either or will get us there. So I'm going to do this one. I'll say, well, what if we take this potential and we divide it by the charge q? So it's the amount of electric potential energy per unit charge. And this ends up being what we define as the electric potential, which we often call voltage, which is really the units, but our electric potential is going to be Q over E delta x, just leaves us with an E delta x. So this electric potential says there's some amount of electric field in this space, and then over some distance that you may move a charge from point A to point B, the change in, that energy, electric field, too many E's, right? It's the electric field times the distance over which a charge is moved, says that's how much electric potential you move through in that space. So this would actually be, honestly, a delta V. It's the change in the potential. We consider that. So then sort of this last piece we can look at here is that, well, we can also do a multiplication by delta x, and we can see that that plays out exactly fine, where we have the electric field times delta x. That's exactly what I've written here. E times delta x is what I'm defining as the potential. Another way we can do it, though, it shows us we actually have a different way of writing electric field at this point, coming from here, where if we come back the other way, if we divide that x back out, we have delta x divided over here. We actually have electric field is equal to delta V over delta x. So electric field, delta V over delta x. Are we lucky? Did that get in the shot? Oh, sort of just barely. So there's two ways to write the field, either force per charge, or it can be potential per distance. This top expression we often use when we want to think in terms of dynamics. If we want to find the force and use Newton's second law, sum of the forces equals mass times acceleration. This bottom one is a lot better for when we have energy considerations. If we want to say, what is the change in electric potential energy, and how does that get converted to, say, kinetic energy? So this energy perspective here, now we can see that, well, since we've defined potential difference as, in a way, as E times delta X, now we can come up to this expression and say, well, that's another way to write U. U is equal to Q times this whole piece, which is delta V. So the electric potential energy can be expressed as the amount of charge that's moving through a set of potential lines, delta V. So Q times delta V. So this is a very important expression for a conservation of energy approach. So that's it. That's our electric square that relates force, field, potential energy, and electric potential.